Hello, this is thermal physics high level. This should take less than 6 hours. In this thermal level physics we will be doing the equation of state, thermodynamic processes, work done, the conservation of energy, which is the first law of thermodynamics, PV diagrams, many of those, the second law of thermodynamics, which is heat goes from hot to cold, and then finishing with entropy, which is the last hour. Okay, the state, the equation of state for an ideal gas is this one. Okay, we have PV equals nRT. Okay, basically the volume in meters cubed, pressure in pascals, N is the number of moles, R is the universal gas constant, T is the temperature of the gas. Because of the way this equation is, we know that the volume is proportional to the temperature. The pressure is proportional to the temperature. It means if you double the temperature, you double the volume, or you double the pressure. There's a relationship between pressure and volume. If the temperature is kept the same, if the pressure goes up, the volume must go down. There's an inverse proportionality between the pressure and the volume. So, yeah. Here we have this difference between an ideal gas and a real gas. An ideal gas is one that follows the assumptions of an ideal gas, such as there is no changing state. That's probably the most important one. As the particles get closer together, they will not tend to change state. They will not tend to join together and make these bonds, which will change a gas into a liquid. An ideal gas will not do that. So there are no forces between the particles, there's no forces between the molecules. The only time there is a force is when they actually collide with each other, and only when they collide with each other. So what happens if we have a gas, a volume of a gas, which is here, and the temperature here. There's a nice linear relationship between the temperature in Kelvin and the volume of a gas. Basically, if you double the temperature, you will double the volume. Okay, there's direct proportionality here. So V is proportional to T. If we have proportionality, we know that there's a straight line graph through the origin. And there we go. This is for an ideal gas. It follows the equation PV equals nRT. However, in a real gas, there are forces that make the particles come together. Not in an ideal gas, but in a real gas. So what will happen as the gas starts to cool down, the volume will get less and less until it basically turns into a liquid. Then the volume will not change, it will stay as a liquid. The volume is not able to change then. So therefore it moves away from being an ideal gas. So here we have it. Yes. So the volume is not proportional to the temperature with a real gas at low volumes, at low temperatures, and at high pressures. Now, if we have this experiment, we do an experiment between the pressure and the temperature of a gas. The volume is kept the constant because it's kept in this glass vessel. We heat up the beaker, so we change the temperature, and see how the pressure changes. We're going to get a set of points roughly like this. We join them up, we get a straight line graph, which does not go through the origin, but nevertheless we have a straight line graph. The equation for this would be y is equal to mx plus c. So this is the straight line graph that we get. Now, if we extend this straight line graph, what happens as the temperature gets colder and colder and colder? What happens to the pressure or the volume? The pressure will get smaller and smaller and smaller and smaller until the pressure becomes zero. effectively the particles stop moving. What will that temperature be then? That will be a temperature minus 273. This is when the particles are moving, have got so little energy, they basically stop moving. This is the lowest temperature that can be obtained, and it's called absolute zero. We still have this uncomfortable relationship where the line intercepts the y-axis. So what we have to do is reset the axis. Instead of starting at 0, which is the melting point of water, of ice, is that we will make it start here instead. It will make it start here instead. Okay, fine. Now we have proportionality. The pressure is proportional to the temperature. Fantastic. It makes the mathematics much easier to be able to deal with. So what is the significance of this point, minus 273? This is the absolute freezer, absolute coldest temperature you can have. We call it 0 Kelvin or 0 degrees absolute. Now we basically, 0 degrees is 273 and 100 degrees is 100 degrees more than that. So it's going to be 373. Now what we have is this absolute zero is a temperature at which it's so cold that the particles in an ideal gas have the lowest energy, lowest level of energy, which means they stop moving, the pressure drops to zero. This means they stop colliding with each other, they stop colliding with the sides of the container, the pressure goes to zero. And it's basically the lowest temperature that we can obtain. Right, here is an example that I want you to try to do. I would pause the display now and try to do this problem. And here is the answer. So start to pause, please. Here we have some other problems. You should try to do these. These are the answers. We will look at these in class. If you want to go to the solutions, you click on this link here. You go to this link here. This will take you to Chris Hamper's webpage where he has the work-throughs, the solutions, not just the answers, but the solutions on how to find the answers to these problems. So we have another problem here, which I would like you to do. We have the answer here too. Here is another problem